Good afternoon, class. Today is Wednesday, June 17th of 2020. This is Coronachem, day 49. Boy, this is starting to sound old. Coronachem. Anyway, your homework was 4 questions. 10, 34, 41, 43, 49. No, sorry, 34, 42, 44, 48. So, first one, they ask, a neon sign is made of glass tubing whose inside diameter is 2.5 centimeters and whose length is 5.5 meters. Oh, I didn't notice that. I thought it was centimeters. Okay, fix it on the fly. If the sign contains neon at a pressure of 1.78 torr at 35 degrees Celsius, how many grams of neon are in the sign? So I solved this problem thinking this was centimeters. It's actually meters, so it means it's 5,000, it's 550 centimeters. It's 100 times more. So this number changes to, let's fix it on the fly. I'm calculating the volume of a cylinder, which is pi r squared h. So basically a cylinder is a circle with height. So here's your circle area, pi r squared, and there's your height. That gives you the volume of the cylinder that results. The radius is 2.5, the diameter is 2.5, so we're interested in the radius, so half of the diameter is right here, 2.5 over 2, so you're going to get 1.25. We're going to square all that, and we're going to multiply the 5.5 meters by 100 centimeters per meter, so you get 550. So this number becomes 1.25 squared times 550 times pi, and what we get is 2.699806 times 10 to the power of 3. So that's 2,000, that's 2,699.806. So that all stays the same, okay? Divide by 1,000 to get liters. Multiply by 1.78. Divide by 760. Divide by 0.082057. And divide by 308.15. And that tells us the volume, which is 10 to the negative 4 moles Let's double check because I don't trust what I just did. Look at it again. 1.25 squared equals, okay, times pi times 550 equals that, or 2,699.806 times 1.78 divided 760 divided 0.082057 divided 308.15, all of that equals, oh, I forgot to divide by 1,000. And we get, yeah, so we get 10 to the negative 4 times the molar mass. So once we found the volume of this 2 centimeters in centimeters cubed, we solve for PV equals nRT. We solve for N by putting PV over RT. We get the number of moles of neon gas. Now we multiply by the molar mass of neon gas, which is times 20.179 grams per mole. So we get this to the power of negative 3 grams. Divide that by multiply by 1,000 to give it in milligrams. And we get 5 milligrams. And what does it say here? Apparently that's correct. You get 5 milligrams. 5 milligrams. So I had the decimal place in the wrong place because I thought this 5.5 was centimeters, not meters. So it makes my answer 100 times bigger than what I had. All right. The next one I asked you to do was 1041. 1041 asks, in an experiment, no, that's the wrong one. 1042 is the one I asked. After the large eruption of Mount St. Helens in 1980, gas samples from the volcano were taken by sampling the downwind gas plume. The unfiltered gas samples were passed over a gold-coated wire coil to absorb mercury present in the gas. The mercury was recovered from the coil by heating it and then analyzed. In one particular set of experiments, scientists found a mercury vapor level of 1,800 nanograms of mercury per cubic meter in the plume at a gas temperature of 10 degrees Celsius. Calculate A, the partial pressure of mercury vapor in the plume, B, the number of mercury atoms per cubic meter in the gas, C, the total mass of mercury emitted per day by the volcano if the daily plume volume was 1,600 kilometers cubed. That's a scary thought that the volcano was belching that much mercury, but as it turns out, the area around the lake has recovered rather impressively. So perhaps it wasn't a particularly toxic form of mercury. I know that organic mercury is extremely toxic, whereas the metallic mercury is not as dangerous, nowhere near as dangerous. You can actually put your hands in it and it won't harm you. What would harm you though is if it was reduced into an organic form, then it could enter your body more easily. Anyway, 1042, PV equals nRT. Therefore, P is equal to nRT over V, and let's enter the numbers. We had 1,800 nanograms of mercury. We should figure out how many moles that is. I don't know if I did that in this problem. Oh yeah, I didn't. It was on the previous page. So we had, before we start doing all this, let's figure out what nanograms of mercury is. 1,800 nanograms of mercury per meter cubed times 1 gram per 10 to the 9 nanograms, so nanograms can cancel, is equal to 1.8 times 10 to the negative 6 grams per meter cubed times 1 meter cubed per 1,000 liters equals 1.8 times 10 to the negative 9 grams per 1 liter. And if we divide that, and if we recall that mercury has a molar mass of 200.59 grams per mole, that gives you 8.97352,809 times 10 to the negative 12 moles of mercury per liter of air sampled near Mount St. Helens, which is the same number times 10 to the negative 9 moles of mercury per cubic meter, because you have to multiply times 1,000 liters per meter cubed to give you that. So same number, except it will have 10 to the negative 9 as its power, in case you're interested. Now, let's go to part A, where it's asking us the partial pressure of the mercury. I'm going to have to erase all this. You'll have to pause it if you want to copy the problem at the appropriate point. But that's the nice thing about doing it on video is I can compress everything into a shorter timeline, and the magic of pause will help you. PV equals nRT, therefore P is equal to nRT over V, and the number we got in the previous calculation, 8.97, etc., times 10 to the negative 12, MG, what the hell? Oh, it's moles, I just wrote it very badly. Moles times 0.08207, 2057 liter atmospheres per Kelvin mole, and no room for the temperature, but it is 283.15 all over 1 liter. So the pressure exerted by the mercury is 2.08494 times 10 to the power of negative 10 atmospheres. Multiply that by 760 torr, not that it really helps because you're still too many orders of magnitude below anything you could really imagine. You get, after sig figs, 1.58 times 10 to the negative 7 torr. Now on part B, they ask, just to recap, the number of mercury atoms per cubic meter in the gas. Well, if you have 8.97, etc., times 10 to the 9 moles of mercury per meter cubed, times an Avogadro's number of atoms per mole, then you're going to have 5.4039 times 10 to the 15 atoms per cubic meter. Atoms of Hg per cubic meter. Or after sig figs, you would say 5.40 times 10 to the 15 atoms Hg per meter cubed. So trillion is 10 to the 12, it's quadrillion. So 5.4 quadrillion atoms of mercury per cubic meter. Now, if you took the entire volume from the size of the plume of Mount St. Helens per day, that was being belched out of the Earth's interior, it was estimated to be, okay, so we had a concentration of 1.8 times 10 to the minus 6 grams of mercury atoms per meter cubed. The plume was 1,600 kilometers cubed in volume, with therefore 1,000 meters per 1 kilometer, but remember to cube the whole thing. So the number is going to be, if you rewrite this part, 1,600 kilometers cubed times 10 to the 3 raised to the power of 3 is 10 to the 9 meters per 1 kilometer. And still multiply by all this, blah, blah. What you get is 2.88 times 10 to the 6 grams times 1 kilogram per 1,000 grams, or 2,880 kilograms per day, or if you like, 2.88 tons of mercury per day were thrown into the atmosphere. That's quite a frightening amount. But mind you, it was spread over a very large area. Okay, that was 42. The next one we were going to do was, oh, I just did your mock test question. So, I misread my own writing. Oh my gosh. I'll give you a different one for the mock test. That was 1042. Okay. Let's do the next one, which is 44. 1044. Hope you guys are actually following along with this stuff. It's going to help you do the test. I don't know how else to help you. This is your last test, so take the time to do it. It'll give you the last little boost you need in your knowledge to do well in university, I think, or at least to have an idea of where you're going.
Which gas is least dense at 1 atmosphere and 298 Kelvin? Remember, Avogadro's law says that any gas, any ideal gas at standard temperature and pressure will occupy 22.41 liters. So they all occupy the same volume. So now all you have to determine which one is the least dense is the one that has the lowest molar mass. And it's a toss-up between sulfur dioxide, HBr, and CO2.
If you look at their molar masses, I can't do those off the top of my head, but you've got HBr. Why did I do that? You've got SO2, you've got HBr, and you've got CO2. So CO2 I know by heart. It's 44.0098 grams per mole. I do so many problems with it that it's embedded in my mind. This one is 64.0588, and the HBr is 80.91194 grams per mole. So the least dense one is the one that has the lowest molar mass. So CO2 is the least dense, and the densest will be the HBr. And it's the same reasoning as the question that we answered yesterday, which was 1043. The next question is
1048. 1048. It says calculate, I'm not sure. Yeah. Calculate the density of sulfur hexafluoride gas at 678 torr and 28 degrees Celsius. B, calculate the molar mass of a vapor that has a density of 7.135 grams per liter at 12 degrees Celsius and 743 torr.
Okay, 1048A then. We're going to use PV equals nRT. And that V is equal to nRT over P. Plug in the numbers that we know. It's for a 1 mole sample. The gas constant, 0.082057 liter atmospheres per Kelvin mole. Temperature is 273.15 plus 28. Remember, we're always converting to the absolute temperature. And then we get 678/760ths of an atmosphere because we're dealing in torr. And what that gives us is a volume of, after sig figs, no, actually there are no sig figs in this one, 27.700, I didn't put it till the very end, 1679. That is the volume in liters of this gas. And the molar mass of sulfur hexafluoride is 146, so SF6, I calculate, I'm not going to show you how to do that part, you should all know that by now. If you don't, I don't know what you're doing. I do know what you're not doing though. Okay, so that would be the molar mass of sulfur hexafluoride, so from there we could find its density. Density equals mass over volume. So if you have a 1 mole sample, that's the mass, right? That's, we assumed a 1 mole sample. So 146 grams divided 27 liters. We'll do that part up here. Density equals mass over volume. We get 146 blah blah over 27.7, etc. The density comes out after sig figs to 5.27 grams per liter. That's what you should get. Now let's do part B. In part B, they say
Calculate the molar mass of a vapor that has a density of, okay, so now they're giving you the density
of the vapor. So it's a two-step calculation. I know there's a formula for it, but don't bother learning it. I didn't learn that formula. You don't need it. You just do a two-step calculation. Here we go. I hate memorizing formulas when they're unnecessary because it just clutters your mind with information that you end up using at the wrong time. Sometimes the less you know, the better. So the pressure of this particular gas is 743 over 760. of an atmosphere. The volume is 1 liter, 0.082057 liter atmospheres per Kelvin mole. And then you get 273.15 plus 12. And what you get is 4.178. 171 times 10 to the minus 2 moles. That's how many moles of the gas you have. And we're told it has a mass of 7.315 grams. So we know that density equals mass over volume. And we assumed a 1 liter sample, so that makes it easy to do the calculation. We have 7.135 grams of the stuff, and it's, oh, they're asking for the molar mass. We're not using density equals mass over volume. We're using molar mass equals grams per 1 mole, sorry. So the grams is 7.135, and the number of moles we just calculated was here, 4.178, etc., times 10 to the minus 2. After sig figs, you get 171 grams per mole for the molar mass of this particular gas. Okay, so that's how you figure that out. That is the last question I wanted to give you for this particular section for the homework. I'm going to give you now a mock test. Work on it tonight. Tomorrow I'll give you the answers to the mock test, and then we can do the final exam for Friday. So I'll give you the questions Friday. You'll have all Friday to work on it, have it into me by 6 p.m. Friday, and then that's it. Bye-bye, have a nice summer, and I'll have your marks Monday, if everything works out. Here's your mark test for tonight. Work on it. Tomorrow morning we'll go over the solutions. It's 10:35. 42, well, look, try to do it without looking, because you already have the answer, I gave it to you. 45, 50, and 66. There's 5 questions in there, but one of them is just a qualitative question, almost, because you're just being asked to find the density of gases. Okay? And we will talk tomorrow when I reveal the answers to the mock test, which should give you enough preparation for the real thing.